flight.
Today
I
we're
would
talking
spread
about
the
integration
cloths
by
under your
parts.
feet,
First, we're going to go
but I,
through the
being poor,
formula, the
have only my
derivation of it,
dreams.
and then we're
I
going
have
to talk
spread my
about the
dreams
tier
under your
listing
feet.
of the functions,
Tread
and
softly,
then how to apply
because
it.
you tread on
And
my
we're going to
dreams.
end with using a table for cases in which you have to use it more than once. We will also cover applications or examples of it, though that may be a separate video depending how long this one runs. Okay, so first of all, the derivation of integration by parts, the formula for it is u dv equals uv minus the integral of v du, where u and v are two different functions of, let's say, x. This comes from product rule. So if I have the derivative of u and v, using product rule, I'd have u prime v plus uv prime. So I'm going to solve for this one, because that's basically this, and move everything else to the other side. And I'll actually rewrite it like that. Same notation, or a different notation, same thing. And now what I'm going to do is integrate both sides. So if I integrate both sides, I have basically u times the integral of dv here, because my dx's are going to cancel. Integrating this will undo the derivative of this, so I have basically uv here, and when I integrate this, I'll have v times du here, because again, when I integrate and multiply by dx, the dx's are going to cancel. And so I basically have the formula for integration by parts. The integration of one function times the derivative of another is equal to both functions minus the integral of the other function times the derivative of the first function. Now, what is my u and what is my dv? Usually, but not always, this will be applied to something that is two functions multiplied together inside an integral. And so we are going to use LIPTE as an acronym to remember which functions we define as u and which functions we define as dv. So let me explain what these are and then how to use the list. L stands for logs, I stands for inverse trig, P stands for power. This is like x to a power. T stands for trig, usually sine and cosine. And E stands for exponential. All of these have known derivatives. The key, though, is that things lower on the list have easier integrals than things higher on the list. And so u is going to be whichever of the two functions multiplied is closer to the top of the list. So for example, if I have x times sine x, trig is below power function. And so here I would define u as x, and d would be everything else, including the dx. To calculate du, I take the derivative. To calculate v, I integrate this, and I don't need the plus c yet. The plus c is something I can tack on at the end without loss of any information. So the integral of sine is negative cosine x. So again, this was my u, and this is my dv. Applying this formula, the integral of u dv is uv minus the integral of v du. So the integral of x sine x dx is x times negative cosine x minus the integral of v du. So now I have gone from an integral I can't do to one that I can do. If I cancel the negatives, the integral of cosine is just sine. And at this point I would put a plus c, and I'll bring the negative out here. Okay? Now, notice that x to the first power was u because it is above trig. It's not always going to be the case that a power function is going to be your u. It could be part of your dv. It all depends upon the relative ranking of the two functions multiplied. So for example, let's say I have the integral of x ln x. Well, logs are higher on the list than power functions. So in this case, u would be natural log of x, and dv would be x dx. Taking the derivative of this, and the integral of this, I now apply my integration by parts formula. And so the integral of x ln x dx will be u times v minus v times du. So this is minus the integral of 1/2 x dx. So now this is fairly easy to do. And that's that. Okay, so where can this go wrong? Well, there are a couple special cases that we have to talk about. First of all, sometimes you will have only a single function inside the integral. In that case, your dv will often be dx. So how do we find the integral of natural log of x? Well, u would be natural log of x, and dv would just be dx. Think of this as sort of like a power function, or if you like, just the easiest thing possible to integrate. Right? 1 is x to the 0, so you can think of it as a power function, and therefore below natural log of x. Or you can just think of it as, well, in the absence of any other choices, that has to be my dv. Take the derivative, the integral, and so it will be u times v minus the integral of v du the integral of 1 is just x. And so that's how we derive the formula for the integral of natural log of x. You can use a similar technique to derive the integral for inverse tan. Now there are a couple other special cases that we have to worry about. One is involving a trig function and an exponential. So if I have, let's say, cosine x times e to the x dx. Well, u should be cosine x, because trig is above exponentials. dv is e to the x dx, and v is e to the x. So if I take the derivative of this, du would be negative sine x. So if I apply this, it's u times v minus the integral of v du. Looks like I'll have to do it again. Again, trig function is u. dv would be e to the x dx again. And so remember, on this side I've got cosine x e to the x dx. Like this. And so I have u times v minus the integral of v du and I'm back where I started. So you could do this an infinite number of times. However, there's a specific trick for an exponential and a trig function. you're going to do it exactly twice. The reason is, when you take two derivatives of cosine, you end up back with cosine, but with a minus sign. Remember, I have the integral on the other side here. So I'm going to actually add this integral to both sides. When I do that, I end up with 2 times the integral on this side. And technically a plus c when I've done the integral. I can write it now. And so now, in order to get the integral, all I have to do is divide by this coefficient. Divide both sides by 2. So the integral of cosine x e to the x dx is 1/2 of this stuff plus c. So again, if you have an exponential and a sine or a cosine, you're going to do this exactly twice. Now, what other cases do you have to worry about? If I had x squared e to the x dx, and I do u equals x squared and dv is equal to e to the x dx, I'm going to end up needing to do integration by parts twice. I'm going to go through it. So it's u times v minus the integral of v du. So again, my u is going to be the x part. I can go ahead and make it 2x. It's fine. So if I apply that, u times v, and I have to be careful with this minus sign, so u times v minus the integral of v du So I'm going to go ahead and distribute that negative and turn that into a plus. And this is now just a simple integral to do. That will just be 2e to the x. And then I have a plus c here. So because it was x squared instead of x, I had to do it twice. If that were an x cubed, I'd have to do it 3 times. If it were an x to the 4th, I would have to do it 4 times. And so when you have x to a power times something that repeats, like a trig function or an exponential, you will have to basically do this as many times as that power until you end up with a constant and therefore something that you can integrate. Now, is there an easier way? Yes, there's an easier way involving tabular integration by parts. Here's how this works. What you do in a problem, and you can do this in all problems, but specifically for problems in which you need to do it more than once, is you identify which part is your u, which part is your dv. So in this case, my u is x squared. So I'm going to write u here, and x squared here. And my dv here is e to the x. I'll ditch the dx. I'm going to be taking derivatives with respect to x until I end up with 0. I'm going to be taking integrals with respect to x until I end up at that 0. Then what I'm going to do is draw lines going down to the right, alternating plus, minus, plus, starting with plus. This represents u times v at each step. And then this would represent u times v from the next step. The sign alternating comes from the fact that at each step we're subtracting v du, and when you do it twice you end up going positive when you distribute that negative. So these signs are going to alternate. All we have to do then is take this sign and then multiply these things. And then once we end up at 0, we're done, because 0 times anything is 0. We just write a plus c. So using this table, my original problem, the answer is x squared e to the x minus 2x e to the x plus 2e to the x plus c. Notice we got there much faster than in this case, but we got the same answer. So you're going to use this especially in problems when you've got x to a power and something that repeats. And you know you're going to do, you know from that exponent being 2 or larger that you're going to need to do it at least twice. Now you can actually use this table for problems in which you don't need to, when you don't have x to a power. You can use it just for integration by parts. You can just use it for problems that are repeated. So let's go through a couple examples for that. Going back to this integral, if I define my u as natural log of x, my dv as x, this is one that's not going to be repeated. I only had to do it once. What happens is the derivative of this is 1 over x. The integral of this is x squared over 2. When you end up with just x's along a row, that's a good sign that the integral of v du will in fact just be an integral of powers of x. So you start the same, plus, and instead of going this way, down, because we only need to do it once in order to get just a product of powers of x, I draw a line this way with a minus sign. This tells me that my answer is the product of these two things minus the integral of these. And so this will get us exactly the same result that we had before. Remember, if you get to a row and there are only powers of x, you do not repeat the process by going down to the right. This is a signal this thing is ready to integrate. And so all I have to do is integrate this product. The line is horizontal, not down to the right, so it is different. We still have to integrate it. This is v du, and so it still needs to be integrated. However, it may be a more convenient way to lay out the information. Last example I'll cover is going back to this repeated example where we had integral of cosine x e to the x dx. We can use the table to do this exactly twice and save us a little bit of work. Not a ton of work, but a little bit. Remember that we end up doing this exactly twice. So we have e to the x here, e to the x here, e to the x here. So this is going to be plus, minus, and then we go across plus. So this integral is e to the x cosine x plus e to the x sine x minus the integral of e to the x cosine x dx. So it's the same setup. We add over, divide by 2, we end up with the same answer. However, because we have to do it twice, the table is probably a little bit less work. Okay, that's it for integration by parts. Please let me know if you have any questions.